Now that we've defined what equilibrium is, we want to be able to characterize it for a given chemical reaction. So if we think about this reaction, 2NO2 goes to N2O4. This is a reaction that very much exists in equilibrium. And I could think about setting up different initial conditions. I could have only NO2, only N2O4, or I could have, say, a mix of them. And so we know that we're always going to reach equilibrium. It's always going to be the same equilibrium. But they're going to look slightly different because we do have different chemical mixtures and things like that. So the actual numbers we end up with might be a little bit different. But we can, if we look at the descriptions of equilibrium that results, we can see some overall trends. One of the things we can see, for example, is that N2O4 concentration is always greater. In this case, that is a product. So our equilibrium mixture has more product than reactant. The NO2 doesn't matter if you started with more or none, you tend to end up with a lower relative amount of NO2 than N2O4 once the system reaches equilibrium. So we can see there's overall trends, but it's not necessarily perfectly the same. So how can we characterize this equilibrium that exists? Since we're looking at relative trends, we can start to think about taking ratios. Okay, that basically there's more N2O4, well, how much more? So if we just take a simple ratio, just the concentration of N2O4 to NO2, we get similar numbers, but not quite right. And we can see that what we end up having to do is take an exponent. We get a 2 if we square the concentration of NO2 once the system reaches equilibrium. We can see that we get the same number every single time, 216. So this is a constant value. So we've said that equilibrium is always the same. This is what is described by being always the same, this 216, this ratio of concentrations with exponents, which come from my reaction equation. So again, reflecting all of the chemistry that's going on here. So this constant value is going to describe what equilibrium looks like. It indicates kind of it indicates the fact, first off, that there's more N2O4 than NO2, and it tells you by how much, right? We know what there's more of, product in this case, and kind of at what ratio, right? What is the relative ratio that we get? And this is getting to the idea of an equilibrium constant. So if I have the reaction, say I have my dummy reaction up there, I can define an equilibrium constant, Kc. So Kc is a number that characterizes my ratio of reactants to products at equilibrium. And the formula for Kc, or my representation for Kc, is always going to look like this. It's always going to be a ratio, and you will note that my products go up top, and it's the concentration of each product in molarity raised to the exponent of the coefficient in the equation. So the coefficient that I had in the equation does still show up here. So it's not like rate orders or we couldn't use it. We want to use those coefficients. We can see that on the bottom is then going to be my reactants. Again, concentration and molarity raised to an exponent equal to the coefficient in the balanced chemical equation. And so the equilibrium constant is a number for each reaction and temperature. If you change the temperature for a reaction, the equilibrium constant does change. And so what this number quantifies is the relative amounts of reactants and products at equilibrium. Not total amounts, because you'll see all of the concentrations do factor in. They are all related via this equation, and they only describe at equilibrium. Right, so when you are at equilibrium, what is it going to look like? What are the relative amounts? Not total amounts, but relative amounts. What are you going to have more of? Reactants or products? That kind of idea. And so because Kc is a ratio, we know it's a ratio with products at the top and reactants on the bottom. So if K is a large number, we know that that means that the top of the fraction is bigger. So that means there is more product at equilibrium. So the idea of what K numerically describes is the relative balance of reactants and products. We said that you have both reactants and products, but not necessarily equal amounts. For a lot of reactions, K is really large. What that means, if K is really big, is that you have, a large volume, almost all of the molecules are products. There's very few reactants left. So we can see the orange is there's just the one reactant that's left over. Very small Ks, which when I say very small K, it's still gonna be greater than 0. So it'd be much less than 1. So say like 0.000001, something like that, means it's mostly reactant at equilibrium. You may come up with a reaction where you have your reactants and they mostly stay the same. You maybe have the product, you maybe get one of those product molecules. And then these intermediate values where K is relatively close to 1. That's where you find an actual mixture, right? We have our product, which there's plenty of product at equilibrium and plenty of reactant at equilibrium. This would be a case where you really do have a true mixture of reactants and products at equilibrium with near equal amounts. So we want to get some practice writing equations for Kc. We're going to do it for the following reactions. I have N2 plus 3H2 becomes 2NH3, and then CO plus H2O becomes CO2 plus H2.
All right, so when we want equations for Kc, so this is our equilibrium constant, and it is a number, but we really also want to be able to come up with the functional form or the equation that relates the value of Kc to our concentrations of all our different components. And so Kc is always going to have a ratio form. So Kc is going to be equal to, and then what we're going to do is the top is going to be the concentration of products, and it's going to be in molarity. So I'm going to use my square brackets so that I only have one product, NH3, so that shows up right there. And then the coefficient becomes the exponent. So this 2 right there becomes the exponent on the NH3 because it's a 2 in the balanced equation. Similarly, on the bottom, I put my reactants. So at concentration of N2, the coefficient there is 1, so no exponent, or just an exponent of 1, so we don't write it. And then H2, and that gives me a 3. So we can see there, there's the 3 that shows up right there. But you can see the general idea is it's always products over reactants. So that's going to be my general shape, and I just write the concentrations for each thing. So CO plus H2O, CO2 plus H2. Always going to be that fraction. Top is products. So I've got CO2, H2, bottom, CO, H2O. And because the coefficients in all of these are 1 across the board, the exponents are all 1. I don't need to write anything. That's totally fine for them just to be 1.
When we're working with equilibrium constants, we're always dealing with these concentrations. It ends up that pure solids and liquids would have constant concentrations, so they're not included in Kc. So for example, this reaction, 3NaOH plus H3PO4 becomes Na3PO4 plus 3H2O. We can see that NaOH is aqueous, H3PO4 is aqueous, Na3PO4 is aqueous. That means they're all dissolved in water. Those are all solutions. They have concentrations that can change. As you approach equilibrium or move around your relative amounts, you would see different amounts of those, and they can then show up in the equilibrium constant. That's why their concentrations show up there. But H2O is a liquid. Therefore, it does not show up in the equilibrium constant. The reason is, if we think about pure water, density of pure water is 1 gram of H2O per 1 milliliter. That can then be converted. You can convert the grams to moles and the milliliters to liters. And it ends up that pure water is 55.5 molar moles of water per 1 liter of water. So pure water has a constant concentration. It doesn't change, so it doesn't show up in these in our equilibrium constants. This is true for all pure solids and pure liquids. They do not show up in our equilibrium constant expression. So let's get some practice. Write equations for Kc for the following reactions. 3NaOH plus H3PO4 becomes Na3PO4 plus 3H2O. Ag plus Cl minus becomes AgCl solid, and FeO solid plus 2CO gas becomes Fe solid plus 2CO2 gas.
All right, so again, we want equations for Kc. And so it's always going to have that same idea where I'm going to expect that Kc is going to be a ratio. I'm going to put products over reactants. But now when I look at my products, I want to check their phases. So that's a Q, so that means it's going to show up, but that's a liquid. Only things that are aqueous gases are going to show up in my expression, because liquids, the concentration doesn't change, right? The whole point of solutions is that you can change their concentration. That's why we spend so much time talking about solutions. They have a lot of utility. So everything that is AQ is going to show up, but the liquid just doesn't appear. So Kc in this case, that's the concentration of Na3PO4. Coefficient, so no exponent. My reactants still show up on the bottom, and I do use both of them because they're both aqueous. So both of them do show up. Ag plus aqueous plus Cl minus aqueous, so silver plus chloride gives me silver chloride. So Kc, got my ratio. I can see that if I look at my products, I only have a solid. So that doesn't show up in the equilibrium expression. So it's just 1. So I just put a 1 there because there's nothing there to show. And so then I divide by Ag plus and Cl minus. So in this case, equilibrium constant is only describing concentrations of silver and chloride. FeO solid, not show up. CO2 gas, that one's good to go. My other gas, but again, the solids, liquids don't show up. Only gases and solutions. So now my Kc is still always going to be the same idea. So that would be a concentration of CO2 squared, and then a concentration of CO squared. And so there we get our nice equilibrium constant expression. I do want to note sometimes, if this is an equation, an algebraic expression, you could factor out the square or combine the whole fraction squared. We don't do that. We just leave it as is. You don't need to worry about algebraically simplifying or do a thing like that with these equations. That, as it's written, is what we would want.
Participation 925, question 2. For each reaction, write the equation for Kc. I have HF aqueous plus H2O liquid becomes F minus aqueous and H3O plus aqueous, and then 2MON solid becomes 2MO solid plus N2 gas. This is the second question on participation 925, due Friday, September 25th at 11:59 p.m. over on Blackboard. Link to the assignment is right below the document where these videos are posted. Again, for each reaction, write the equation for Kc. When you're writing equations for Kc, if you're writing in the Blackboard text editor, don't worry too much about subscripts, superscripts, numerators, denominators. Just kind of get the right thing. Now, if you're handwriting, like you will on the test, all the formatting needs to be correct. But it's those two reactions: hydrofluoric acid and water make fluoride and hydronium, and then the molybdenum 3 nitride makes molybdenum and nitrogen. All right, got a question for participation 925 in this video. Got more videos to go, more questions to find. See you in the next one.